How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at structures and bonding of solids practice problems. So number one, it says on a face-centered cubic unit cell, what fraction of volume of each corner atom is actually within the cubic unit cell? Now for this, it doesn't really even matter that it's a face-centered cubic cell because each corner for any cubic structure is going to have the same kind of experience. So let's say I have my cubic structure quickly drawn here. At each corner, there was one whole atom. But in order to make the unit cell, I had to cut that atom in half this way to make that face. I had to cut it in half again to make this face. And I had to cut it in half again to make this other face. So if I'm cutting something in half 3 times, I got half of a half of a half. That tells me that I have 1/8 of an atom at each corner. So 1/8. Right, CsCl crystallizes in a unit cell that contains a Cs+ ion in the center of a cube and a Cl- at each corner. What type of unit cell does CsCl form? So, all right, let me quickly draw my cubic structure. Boom, boom. And it's saying that in the center, there is a Cs ion. And that at each corner, there is a chloride ion. So what am I showing here? Well, let's see. I have a cubic structure with an atom in the middle. We call that a body-centered cubic structure. So it's body-centered cubic. That's a B. That is a B, as in body. All right, number 3. CsCl crystallizes into a unit cell that contains Cs. Right. All right. So same thing as before, but it says how many of each are there. All right. Well, if I'm drawing my cubic structure again, because I love drawing cubic structures, I know that in the middle there is one full Cs+ ion. So there's one Cs+ ion. And then at each of the corners, there is 1/8 of a Cl-. But how many corners are in a cube? There are a total of 8. So I times that by 8 and I end up with one full chloride ion in each unit cell. So 1 and 1. 4, a metal crystallizes in a simple cubic structure with a unit cell edge length of 4.6 angstroms. What is the radius of the metal atom in angstroms? So it's saying, hey, if I'm looking at a simple cubic structure, let me just look at one face. At each corner, I have a part of an atom, right? It's hard, all right? I'm not very good at art, but when you draw it like this, they're touching right in the middle, which tells me that from the corner to the middle is 1 atomic radius. And then again, from the middle to the opposite corner is another atomic radius. So one side is as long as 2 atomic radii, or 1 atomic or a diameter. So if it's asking for the radius, well, 4.6 angstroms has to equal 2 radii. So I just do a little division and I end up with 2.30 angstroms is my atomic radius. All right, not so bad. All right, 5. What is the radius of a gallium atom if its solid forms a simple cubic structure with a unit cell of 3.7 angstroms? So again, keeping it simple for y'all with these examples, no face-centered ones, but here we go. So again, they meet in the middle. From the corner to the middle on either side is 1 atomic radius. From the middle to the opposite corner is another one. So I really just got to divide that by 2, and I end up with, 1.85 angstroms. All right, and then, yeah, it's not so bad. Number 6, which of the following options is not a type of solid? Ionic solids? Yeah, they're a thing for sure. Yes, that is a thing. I'm going to call that true. Molecular solids? Yeah, that's like ice. A molecule forming a solid. That is also a type of thing. Covalent network, like a diamond. Yes, that is a type of solid. Metallic? Yes, that is also a type of solid. Supercritical? Ooh, nope. That one is not a type of solid. All right. Number 7, what type of solids consist of atoms or molecules held together by dipole-dipole forces, London dispersion forces, and or hydrogen bonds? Interesting. So atoms or molecules held together by all of these attractive forces are for covalent compounds or molecular compounds. right? That's what's holding those molecules together. So if I'm looking, it's going to be choice D, as in David. All right, if I take a look, ionic held together by electrostatic or ionic bondings. Covalent networks, it's held together only by covalent bonds. There's no intermolecular attractive forces. Metallic solids are held together by metallic bonds. And then metallic and covalent network, I would say definitely not covalent network because they're only covalent bonds. No attractive forces, they're just held together by covalent bonds. So best answer would be choice D. All right, I hope you found it helpful. I'll see you in class. Okay, bye.